Well, we have f at x plus h minus f at x all over h. Or really, we're just taking x plus h and squaring that, because instead of just having f at x would be x squared, but we're substituting x plus h for x. So we get the quantity of x plus h squared. So now that we have this, we can continue to simplify this and get a relatively simple formula for the derivative of x squared. And then we could quickly use that to get the slope at really any point. So we'd get this, and once again, these two terms cross off, because it's x squared minus x squared, that's just 0. And then 2hx plus h squared over h. Well, we can do the same thing here like we did here with the crossing off these terms. And say, really this is just the limit as h approaches 0 of 2x plus h. And so this would really be the formula we can use for the derivative, or to find the slope, which is really equal to 2x. So we know that 2x is, by definition, the derivative of x squared. And there are many different ways of writing this. We can say d over dx. This is a very common notation for derivative, or change in over change in x. And we can think of this as a differential operator, because it's finding change in over change in x, or the derivative of x squared. Or, in this case it's x squared. So to put it simply, d over dx of x squared equals 2x. Okay, so today we will be temporarily suspending our lessons on limits to get back to these rules for differentiation, which will be very important for you to know in the future. Now, let me just say, for these rules of differentiation, we assume that c and m are both constant values, and u and v are differentiable functions of x. Now, rule number 1 would be that if we take the derivative, symbolized by d over dx, of a constant c, all we get is 0. And that is because, imagine if we had a function, f of x equals c, some constant, like 3 or 5. Really, all that would be, if we were to graph it, is just one flat straight line. Because no matter what x is, f of x is this one value, like 5 or 7 or 10, or just one constant value. Therefore, it has to be a straight line, and it has to have a slope of 0, which means if we take the derivative, we'll just find 0. Now, for the next rule of differentiation, if we take the derivative of mx, for example, some constant value times x, we really just get m, and this can be proven using the formal definition, but if you just consider a graph similar to the last one, if we had function of x equal to 2x, a line with a slope of just 2, then we know that the slope throughout this whole line is really just equal to 2 in this case, or, whatever constant value it is, because it's linear, and so the value of the derivative is just that constant, that coefficient of x, which is m, Okay, so now for the third rule. D over dx of, and this rule is very special, it's known as the power rule. If we take the derivative of x to the m, we get m times the quantity of x to the m minus 1. And this one's very, like I said, very common, very useful in mathematics, and yeah, good one to remember. Now what we can do now, I'm going to skip ahead a little and say that what if we had the derivative of the product u times v? Now this is what's known as the product rule, and it's pretty important to remember, along with the quotient rule, which I'll do next. But the product rule states that if we take the derivative of a product of two functions, really what that is well, let's analyze this formula for a second. We basically take the second function here, the latter differentiable function, multiply it by the derivative of u, and we add u times the derivative of v. So it's relatively straightforward. So I'm going to label this product rule. So that's the product rule. And then we can say something similar for d over dx of quantity of u divided by v, which is the quotient rule. So we know that this would be v times the derivative of u minus, we have minus here, u times the derivative of v. And we divide all of that by the quantity v squared. And that is what's known as the quotient rule. So now that we've seen all the rules, I'm going to do some practice with these. And say, first, what if we had the derivative of 3x cubed minus 4x squared plus 5x minus 1,700? And so this would be equal to, well, let's think about it. Well, in this case, we can basically say that since 3 is a coefficient, we can basically take it out temporarily. Just take out that coefficient and consider just the derivative of x cubed. Well, if we have the derivative of x cubed, we should certainly look back to this power rule that I said was important up here. So we have, in this case, m equals 3. We get x to the third. So we bring down the exponent, 3, and then decrement that same exponent. So we get 3 times x to the 3 minus 1, which is really x squared. So 3x squared. And so we can apply that rule here, and we say 3 times x squared. Minus, and then we just keep going to the next term. Okay, so think about taking the derivative of negative 4x squared. Well, once again, we bring down the exponent, and we get 4 times 2 times x to the 2 minus 1, so that's just 1. And then coefficient of 5x, that's just 5, so we can say plus 5. This is just a constant, so we get rid of it when taking the derivative. So after simplifying, we get 9x squared minus 8x plus 5. And that is our derivative. So if we've applied the corresponding rules in order to find the formula for the slope of this function. So it's really pretty cool.